Okay, this is going to be our chapter 5.2 lecture for the electron arrangement in atoms, and we're going to start building our electron configurations based on the rules of electron configuration. So, first thing we have this is our objective: is we will exhibit knowledge of the rules governing electron configuration, or in other words, what are the three rules for writing electron configuration of the elements? And the other thing I want you to be able to answer is, why do actual electron configurations for some elements differ from those assigned using the Aufbau principle, which we're going to get to in just a minute. Now, first objective, students will exhibit knowledge of the rules governing electron configuration. So, electron configuration, electron configurations represent a distribution of electrons and their energy levels, sublevels, and orbitals to be filled for a given atom. Okay, and the way we determine the electron configuration is we use the Aufbau principle, German word. Again, not sure what it means. I'll look it up for you some other point. The Aufbau principle: electrons are added to the lowest energy orbitals until all electrons have been accounted for. So as you move up through your electrons, you have a number of different. As you move up through across the periodic table, across all of our elements, we have a number of different electrons, and they all have to be accounted for in the electron configuration. So, this is the first part of the Aufbau principle, is that we start from the bottom up, and all of the electrons have to be accounted for. Second, there is the Pauli exclusion principle. I'm not referring to Rocky's, slime bag brother-in-law. I'm talking about the Wolfgang Pauli exclusion principle, that orbitals can hold a maximum of 2 electrons, and they must be of opposite spin. The idea behind this is if you have an electron that is spinning. If you have an electron spinning this direction and you have another electron spinning that direction, they create the magnetic fields that will be opposite. They'll create magnetic fields that are opposite to each other, and so there's a slight attraction, and they can actually tolerate each other in the same presence, even though they both have a negative charge. If they were to have spin in the same direction, then they would no longer tolerate each other, because not only would they both have negative charge, but they would also have similar magnetic fields, and they'd really push each other out. So, that is the Pauli exclusion principle. And then finally, there's Hund's rule. Hund's rule says the electrons occupy energy orbitals so that a maximum number of unpaired electrons result. And equal energy orbitals always have unpaired electrons of the same spin. Alright. So, here's how we go with this. We start with our orbital diagram. Okay, and we start filling in electrons to match our orbital diagram. Okay, now carbon. Carbon is going to have 6 electrons. Now, according to these rules, according to the Aufbau principle, electrons added to the lowest energy levels, orbitals can hold a maximum of 2 electrons. They occupy energy orbitals until we have a maximum number of unpaired electrons result, and they always have unpaired electrons of the same spin. Well, the first energy level is 1s right here. So we're going to draw our first electron, and this is what our electrons look like. They look like the streak 7. Okay, but to fill this energy level, we always fill the lowest energy levels first. So before we can go on to number 2, we finish with number 1. And then they have to have opposite spin. Opposite spin. So, our carbon right here is going to have, let me draw that a little more neatly. Our carbon is going to have, in the 1s orbital, an electron going up and an electron going down for our 2 kinds of spin. Then we have the 2s orbital, because we still have 4 more electrons to go. This is 1 electron, 2 electrons. Those are going to go there because this is talking about the lowest energy orbital, and S is a lower energy orbital than P. Okay. Then finally, we're going to take our, then we move on to the Hund's rule because we still have 2 electrons to go. And electrons occupy equal energy orbitals so that a maximum number of unpaired electrons results. Well, we only have 2 electrons left, so they're going to have to go into their own separate orbital. Now that's carbon. Now iron gets a little tricky, and so what we're going to do with iron is I'm going to give you a better visualization of what iron is going to be. So we'll pause here, or we'll pause and so I want you to check out this. This is a diagram showing the increasing energy of all of our sublevels and orbitals, and these are all of them that we have in there. Now carbon was up and down, and then we went to the next energy level orbital, up, down, and then we went to the next one, which was up and up. Now you could have done down and down, but by convention, we just decided to do up just to keep it consistent with all the other ones, and that was carbon. Okay, 6 electrons in our carbon. Now, for iron, iron has 26 electrons. So we're going to need to follow the same rules and go through all 26 electrons. And to start with, that is going to be up, down, there, and an up, down, there, because we fill those 2 lowest energy orbitals. Then, according to Hund's rule, we have to maximize our number of unpaired electrons before we can start pairing them. Well, we still have a long ways to go. We have 26 electrons to fill in, so we're going to fill in up, 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 down, 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 according to Hund's rule. We do maximum first, and then we fill in the orbital, and then we go to the next lowest energy level, which is going to be 3s, and that's going to go up and down. We fill it up, and right now we're looking at 12 electrons. 12 electrons. But we're not done. Okay, so we're looking for 26. And so the next lowest energy level orbitals are the 3p. And so we will put up, and an up, and an up, and then a down, and a down, and a down. Because remember, they have to have opposite spin. They're in the lowest energy levels first. And you put 1 electron in each energy level before you have an unpaired electron in each energy level before you start pairing them up. Okay, and that has us through 2, 4, 6, 8, 10, 12, 14, 16, 18. We only have 8 more to go. Now here's where we get a little tricky. Next lowest energy level, according to the diagram, is 4s. 19, 20. But after 4s comes 3d and not 4p. So the 3d energy sublevel, because remember, the first time we ever see a d orbital is in the 1s, 2sp, 3sp. D is in the 3rd energy level. So we have 6 electrons left, and we fill them out so that they're the maximum number of unpaired electrons. And the way we make sure of that is we put 1 electron of everything that we've got into each d orbital. Now we're at 25 electrons, and then we finish with 26. And that's all of our electrons. That is 26 electrons. And so the electron configuration for iron is then going to be, and this is iron, not carbon, carbon, is iron. The electron configuration for iron is then going to be 1s2, with 2 electrons there. 2s2, because we have 2 electrons there. This will be 2p6, because we have 2, 4, 6 electrons. 3s2, 3p6, 4s2, and 3d. Oh, sorry, not 10. 3d. Okay, and that's how we make our electron configuration for iron, and we use the Aufbau diagram to show us where electrons are going to go first. Now, what you should do then is track using the Aufbau diagram to see where they are in the periodic table, but we'll get to those in a minute. Okay, now you may have noticed in the previous diagram that 4s actually fills before 3d. Okay, this is because there's some electron overlap, and the energy of a 4s suborbital or sublevel is actually less than the energy that it takes to go into a 3d sublevel. And it just occurs because as we're adding more and more levels and we have simple wave patterns and complicated wave patterns, that there's just a little bit of energy overlap right there. Now, occasionally this occurs when electrons will fill in a higher energy sublevel, skipping other sublevels to reduce electron repulsion, and this achieves a more stable atomic structure. Which brings us to the electron configurations. Now, we already wrote one for the iron, but we're going to write some more. So, electron configurations are similar to the orbital diagram, but they're easier because you don't actually have to draw each and every arrow for your electrons. By the way, this is our next objective. Students will write correct electron configurations for the most common element. So, our notation is this. This is 2p5. 2 is the major energy level. P is the sublevel. 5 is the number of electrons in the 3 possible orbitals of the P sublevel. Okay, so what you guys are going to do is write the electron configurations of the first 20 elements. Okay, now, I'm going to do the first one for you because I'm nice like that. Hydrogen is atomic number 1. It has 1 proton, and therefore it has 1 electron for the neutrally charged atom. The electron configuration, then, is the placement of the electron. And that first electron is going to go in the first energy level, the S sublevel, because it's the only one the first energy level has, and the 1 in superscript. This is a superscript. This is not an exponent. Not an exponent. Let me say that again. Words so plain and clear to command your assent. This is not an exponent. That 1 right there is not an exponent. You don't say 1s to the first. You don't say 1s to the first. You just don't say that. You do not say 1s to the first. You would say 1s1. That's it. You do not say 1s to the first. You would say 1s1. Is the electron configuration for your helium. Now, what you guys are going to do is go through the next 20. So I'm going to pause here again, and you guys I'm going to pause here as you guys go through these 20. And this will give you, this little diagram over here will give you a hint where you need to go. So when this is done, or when you guys are done with this, then we'll come back and we'll finish. All right. Back. See how you did. If hydrogen was 1s1, helium would be 1s2. Then lithium would be 1s2, 2s1. Beryllium is going to be 1s2, 2s2. Boron, 1s1, 2s2, 2p1. Carbon 2p2, nitrogen 2p3, oxygen 2p4, chlorine 2p5, 2p6. 2s2, 2p6. Neon, however, fills the 2 orbitals. Fills the second energy level, the 2s2, 2p6, is filled with electrons. That makes neon kind of special and holds a special place for us because this is a very stable electron configuration. Because of that, we now use this neon as shortcut over here. It becomes neon 3s1, neon 3s2, neon 3s3, 3p1, 3p2, 3p4, 3p5, 3p7. Oh, there's 3p6 again. My bad. 3s2, 3p6. We finished there. And all of a sudden we're on argon. Well, look at where argon is on the periodic table. Argon's all the way to the left, all the way to the right. Again, holds a very special place. And so the next thing all the way to the left is krypton, and we're going to use for it argon, because that means neon, which that means 1s2, 2s2, 2p6, 3s6, 4s1. Calcium would be argon, 4s1. Okay, then to finish this section, notice that the 4s filled before 3d because that electron overlap. And so I want to refer you guys back to this diagram where we wound up with after argon, which was argon was going to be up, down, up, down, up, down, or I'm sorry, up, 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 down, 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 up, down, up, down, up, up, down, down. Yeah, those should all be up first and then all down. That winds us, that has 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons, which means 18 protons, which means atomic number 18, which means argon. Argon is one of the noble gases all the way over there to the right of your periodic table. And every single time that we fill up a p orbital, we're going to have a noble gas. But then after that happens, then the next one we're going to fill is this 4s orbital because there's a little bit of overlap between the 4s and the 4d. See, here's all of your 4s. Right? And here's your last 3d, but there's a little bit of overlap because 4s is going to fill up before 3d. Okay, that is the end of chapter of 5.1. And let's get to work on the rest of that homework. Right there. And this will be your homework for section 5.2. So let's get that stuff done. Please make sure you adapt your homework cover sheet. The book assignment is going to be 30 through 39, all on page 149. And you need to complete your section review 5.2. So that's it for 5.2, and stay tuned for 5.3.